In this chapter or this section, we're going to talk about phase changes. So changes between the different states of matter. Okay. So when we talk about phase changes, we always have to start with talking about energy, because energy is really kind of what drives these changes. So energy is the ability to change or move matter. In other words, it's the ability to do work. Okay, so kinetic energy is the energy of motion, and temperature is a measure of the average kinetic energy of a substance. Okay, so this goes back to the whole the atoms are vibrating in place thing. Okay, so the vibration is basically used to take a temperature measurement. Okay, so thermal energy is the total kinetic energy of a substance. Now that will depend on the amount of the substance present. Okay, the kinetic energy really just kind of depends on the substance itself, not necessarily the amount there. So in other words, steam has a higher temperature, so it has a higher kinetic energy. Okay, but the ocean, even though it is liquid, has a higher thermal energy. Okay, so if you think about just the steam that's coming off of a pot that's boiling on your stove, okay, you've got a higher temperature, there's a higher average kinetic energy coming out there because it is a gaseous state. Okay, it is the gas form. But then in the ocean, even though it's at a lower temperature, there is just so much more of it. So it has a higher thermal energy. So during phase changes, the energy of the substance changes, but the identity of the substance will not change. Okay, so if you've got carbon dioxide that's going from solid to a liquid, okay, it's still going to be carbon dioxide. Right? That is not going to change. It's just the state, the phase of the matter that changes. So changes of state that require energy, okay, you can have a bunch of different ones. So you have evaporation or boiling. Those take your liquid to a gas, okay. You can also have melting, and that's solid to a liquid. And then you can have going straight from a solid to a gas, which is called sublimation. Okay, so I've got a video, it's the time warp one of the dry ice. Okay, that is showing you an example of sublimation and how energetic that can be. Okay, how much energy is involved in that. And then there is also kind of the release of energy. So this is the opposite. This is when you're basically going from a freer state, like a gas, to a more restricted state like a solid. So condensation is gas to liquid. So you see this when you have like a drink of water and it's got ice in it, and then there is some liquid that forms on the outside of the glass. Okay, so the ice there is reducing the temperature of the water in the air around the glass, which creates that condensation. Okay, and then you also have freezing. So in this case, you are going from a liquid to a solid. So you are, again, releasing that energy to go to a more restrictive state. And then there is also gas to a solid. So you can go straight from a gas to a solid in what's called deposition. So deposition is one we don't normally see all that often. Okay, so I do have another video example of a deposition. Okay. So the one thing to remember about phase changes, so you are going to have energy changing throughout the entire thing, but during a phase change, temperature will not change. Okay, this is one thing that a lot of people get screwed up, okay, because it doesn't really seem, it's kind of counterintuitive. It's not exactly what you would expect when you're looking at it, okay, but if you look at this, okay, so we start at negative 50 degrees Celsius. So this is the phase change of water, so that is definitely a solid, okay? And then as you start increasing the amount of energy that goes into this, you are also increasing temperature. But once it gets to 0 degrees Celsius, the melting point of ice, Okay, that's where that temperature change stops. So all of the energy that is continuing to be poured into this ice is going straight to converting that ice to water. Okay, and the temperature won't start increasing again until all of that ice is now in the liquid state of water. Okay, so it takes quite a bit of energy to get those particles moving around enough that they actually go to the liquid state. And that's why the temperature doesn't rise. Now, once you have all of that ice converted into water, that's when your temperature is going to start going up again. Okay, and then you get to 100 degrees Celsius, the boiling point of water. So again, at this point, it's going to start going through a phase change. Okay, and you can see it takes a lot more energy to change that same amount of water from a liquid to a gas. Okay, so when we were melting all that ice, it wasn't in that state for very long, that kind of transition state. But when you get up to boiling the water, it's going to take quite a bit of energy to take it up to the next step, to convert it all into steam. Okay, and so that's where all of that energy is going. Now, once it finally transitions from a solid or a liquid to a gas, that's when you can start increasing the temperature again. Okay, but it's not going to start increasing that temperature until it is all gas. So this is always kind of a weird concept to think about. All right, so conservation. There are two conservation laws that go right along with this subject. So there's the conservation of matter, which states that matter cannot be created or destroyed. It can be changed, it can be converted, and you can use energy to do a bunch of different things to it. Okay? But then when you get to energy, there's also the conservation of energy. Energy cannot be created or destroyed either. It can be released, it can be absorbed, it can be changed. You have different states or different types of energy like kinetic, potential, light energy, heat energy, different things like that. Okay, so you can change it and you can move it around and have it do things, but your energy levels are always going to remain constant and your matter levels are always going to remain constant. Okay, now in very weird cases, you can actually convert matter and energy. Okay, but this is something that is incredibly difficult. It doesn't really happen. Okay, it's more theoretical at this point, but it goes along with Einstein's theory of relativity, the E equals mc squared. So you matter unless you multiply yourself by the speed of light squared, then you energy. I might have used that one before, but it's obviously one of my favorites. I love it. Okay, so that is the end of this section, I think. Yep, all right.